What's up, it's Tikhonov, and this is the second episode of concept-based chemistry where I'm gonna give you the essential background knowledge that you gotta have in order to understand my course. I know in the first episode I said that you should have zero chemistry knowledge in order to understand this course, but I didn't say anything about other disciplines such as physics or math. These two subjects are foundational in order for you to understand my course, and that's why today I'm gonna go through some key concepts, key ideas from physics and from math. So if you're ready, let's dive in. So the first subject that we're gonna cover is physics, and the first topic from the subject is electrostatic force, also known as Coulomb force. This is the force of attraction between opposite charges, as it is right here, you know, the minus and plus charges, and the same force is the force of repulsion between the same charges. For example, two negative charges or two positive charges. This force is proportional to the values of those charges, and it is inversely proportional to the square of the distance between their centers. This is very important. Not between their surfaces, but between their centers. By the way, this means the same as this formula. This is just a sign which denotes that F is proportional to this thing. The next important thing that we're going to talk about is kinetic and potential energy, and energy in general. So here you can see this nice little dumbbell which is falling to the ground, and here imagine that someone holds it like this and it is not falling right away. In this position, its kinetic energy is zero and its potential energy is more than zero. So what is kinetic energy and what is potential energy? Kinetic energy is basically the energy of movement. If any object is moving, it has a non-zero kinetic energy. If it is staying at the same point but it is rotating, it also will have kinetic energy. Potential energy, on the other hand, is the energy that is capable to cause movement. So as you can see, in this case, potential energy is proportional to the height above the ground at which the dumbbell is located. Right here, it has a non-zero, a positive potential energy, but a zero kinetic energy. If we let it go, then right here, right when it touches the ground, its kinetic energy will be non-zero, it will be greater than zero, but its potential energy will become zero. So what happened here is all the potential energy was converted into kinetic energy. The direct analogy of this situation is right here. Here you can see two charged particles, one of which is held by a human hand, and in this position it has a non-zero potential energy because this charge attracts this charge using Coulomb force that we have just talked about, and this is why here it has a non-zero potential energy but zero kinetic energy because it is not moving right here. As we let it go, its potential energy gradually becomes converted into kinetic energy until it is used up. It will become used up when this charge will drop to the surface of the positive charge. The important thing is that the kinetic and potential energies added together give the full energy, which essentially stays at a constant value if there are no external sources of energy. This leads us nicely to the third important concept from physics, which is work. Basically, when we do work on an object, we change either its potential energy or its kinetic energy, or both of them at the same time. As you can see in the example right here, with the same dumbbell, if we take the dumbbell, which has the potential energy 1, which is 0 joules, by the way, energy is measured in joules, both kinetic and potential energies. If we take this dumbbell and we lift it at a certain height above the ground, we do work on it because we increase its potential energy. And that's why EP2 is greater than 0, because we have done work on this object. If we were able to calculate the potential energies of the dumbbell at any height, we would be able to calculate the work we would do on this dumbbell when lifting it from height 1 to height 2 by just subtracting the corresponding potential energies. So in the real world, it looks like this. Here you can see a pretty heavy dumbbell, and right here it has 1 potential energy, while right here its potential energy is much greater than it was right here. When I do this, I do work on the dumbbell. By the way, when I let the dumbbell drop, I let the gravity do work on this dumbbell, because the gravity also changes its potential energy, but it lowers its potential energy, while I was actually increasing its potential energy. That's why the work done on an object can be negative or positive. The next concept that we're going to talk about is electric field. Any charged particle or any charged body, including point charges, which are basically charged particles which are infinitely small as a dot, can generate electric field, and they do generate it always. They generate electric field in every point in 3D space around them, and this electric field at any of those points is proportional to the charge of the body generating the electric field, and is inversely proportional to the square of the distance between the center of this charged body and the point in space where we measure it. Well, what is its center? The important point here is that any number of charges, including any number of point charges, generate electric field around them. And this electric field, in 100% of the cases, is equivalent to the electric field that would be generated by 1 point charge somewhere in the center of the charged body. Well, the precise location of this point charge will depend on the charge distribution inside this charged body, but usually it is somewhere in the center. And so when the negative particle is attracted to this charged body, it is actually attracted to 1 point inside of this body, which is its center. Now, here we can also say that the electric field generated by this charged body changes the kinetic energy of this negatively charged particle. But the truth is that, as in the very first case with the dumbbell, here the potential energy of this negatively charged particle is being gradually converted into its kinetic energy, and that's why it is gaining velocity while losing potential energy. Nevertheless, it can be said that the electric field does work on this negatively charged particle to transfer it from 1 point in space to another. Now, electric potential, which is the next topic from physics that we're about to cover, is defined as the work needed to be done on a sample positive charge equal to 1 Coulomb. By the way, charges are measured in coulombs, to transfer it from an infinite distance from the object generating the electric field to a point in space where we measure the electric potential. Okay, so here, because the charged body generating the field is positively charged, this work will be positive because it will repel any sample positive charges that we will be trying to transfer from an infinite distance to any point around the big positively charged body, okay? So electric potential is actually proportional to the charge of the body generating the electric field, and it is inversely proportional to the distance between the center of the object generating the field and the point in space where we measure the electric potential. Now, the work needed to be done on a point charge in order to transfer it from one point in the electric field to another point in the electric field can be calculated as the potential difference between these 2 points multiplied by the magnitude of the charge of the particle being transferred. Now, if we look at the potential difference between 2 points in space inside a wire in an electric circuit, we will arrive at the Ohm's law, which states that the voltage, which is basically the potential difference between any 2 points in a wire, is proportional to the current through this wire. It is also called the intensity of current, which is basically the speed with which electrons travel inside the wire. The proportionality coefficient right here is called resistance, and the longer the wire, the greater will be the resistance, and the shorter the wire, the less it will be. Electrons are negatively charged particles which are super small, and we will talk about them in great detail in the next lecture, but for now just assume that in any wire which is made of metal, usually there are those negatively charged particles called electrons that move inside it because they're charged, and inside a wire there is an electric field. The important point here is that when electrons are placed in an electric field, they will move from a point with a lower potential to a point with a higher potential. This concept is actually important for redox reactions, which we'll talk about in subsequent lectures. Now it is time to talk about magnetic field, but before we dive into the whole topic of magnetic field, I would like to introduce you to the drawings of electric field. So here we can see 2 charges, the positive charge and the negative charge. Each creates its own electric field, and it is usually drawn as the lines with arrows, where arrows indicate the direction of movement of positive charges that would result from placing them inside the given field. So as you can see, in the case of the field generated by the positive charge, the arrows point away from the center of the charge, while in the case of the negative charge, the arrows point directly to the center of this charge, because negative charges attract positive charges. Now, we're moving on to talk about the magnetic field, and the magnetic field is basically drawn in the same way as the electric field, but there are no magnetic charges, okay? Those single charges are actually called monopoles, because there's only one charge here in each case. Well, there are no magnetic monopoles. Okay, so these lines do not indicate movements of any magnetic charges, because magnetic charges do not exist on their own. But every object that generates magnetic field has its own magnetic moment, which is denoted m here. And the property of this magnetic moment is that if this body was placed in an external magnetic field, it would orient itself so that its magnetic moment would become aligned with the external magnetic field. And this is what the arrows indicate in the case of the magnetic field. Okay, so as I said, there is no such thing as a magnetic monopole, and right here we were actually talking about a magnetic dipole which had a north pole and a south pole. Analogously, for electric charges, we can also define a dipole, an electric dipole, which can be formed from two opposite charges that are in some way attached to each other, but at the same time are kept at a constant distance from each other. Every electric dipole is characterized by its dipole moment, which is another vector quantity, and it is equal to the distance between the centers of these two charges multiplied by the magnitude of those charges. So the greater the absolute value of the charges, the greater is the dipole moment, and the farther they are apart, the greater the dipole moment. In chemistry, electric dipoles will give rise to polarization and polarized molecules, which is very important for chemistry, so make sure that you understand what I'm talking about here. Okay, now that we have talked about electric fields and magnetic fields, it is time to see how they are interconnected. So the concept is this: any moving charge will always generate magnetic field around it, and any changing magnetic field will generate the movement of charge. So to illustrate this, let's look at this example. Here we have a circular circuit, all right, with a battery that is generating electric current in the circular wire, and this electric current will generate magnetic field in its turn. But if we just look at a wire, it will generate the magnetic field as I've shown here. But if we take a circular wire frame and we apply a changing external magnetic field to it, this would result in an electric current inside the wire, even if there was no battery in the circuit. So at this point, I gotta introduce you to the direction of current. So for historical reasons, the direction of current is actually the direction that the positive charges would move in a given wire under the given conditions. So I know this is counterintuitive. You are thinking right now, the current is the movement of electrons. Electrons are negatively charged, so why the current shows the movement of positive particles? You see, people didn't always know that the current is the movement of electrons. And at some point, they already knew that there is some kind of a current inside wires, but they didn't know what particles are moving there, so they just assigned them a positive charge. So this is why it is so. So once again, remember that the direction of current is the direction that the positively charged particles would move inside a wire under the given conditions. Okay, now it is time to introduce you to a useful mnemonic which is called the right hand rule. The rule is this: if we take our right hand and we imagine that our thumb is the direction of the current, remember this is where the positive particles would move, then the four curled fingers would indicate the direction of magnetic field around the moving charges, right? The magnetic field that would be generated by the movement of charges. So in this example, we've got a wire and the electrons flow from the whiteboard towards the camera. The current will actually point in the opposite direction. You know that this is for historical reasons, okay? And so as the current is facing the whiteboard, the magnetic field generated will be aligned with the four curled fingers. So it will go just as I've shown here. Now let's get back to a wire in which we can induce a current by applying a changing magnetic field to it. So if we apply a changing magnetic field to a circular wire, this will generate an electric current inside this wire, so that the magnetic field generated by this current will cancel out some of the external magnetic field. So if the external magnetic field is directed as shown and its magnitude is increasing, then the current inside a wire will try to lower that increase in magnetic field magnitude by creating its own magnetic field. And we can apply the right-hand rule here too. So if we know that the magnetic field, the external magnetic field, is increasing this way, it means that the magnetic field generated by the wire will be pointing upwards. And for it to point upwards, the current in the circular wire should flow in this direction. So if we looked at the wire from the top, the current would go anti-clockwise. Okay? So as you can see here, the electrons will move in the opposite direction. So if we see from the top, they will move clockwise. Now, while the electromagnetism is critical in the nuclear magnetic resonance spectroscopy that we are going to talk about, the most important thing in electromagnetism, the culmination, the pinnacle of electromagnetism, is an electromagnetic wave. So what is an electromagnetic wave? Actually, the electromagnetic wave is just two fields, electric field and a magnetic field, and they both fluctuate simultaneously in perpendicular planes, generating each other. Okay? One field cannot exist without another. This is why it is sometimes called an electromagnetic field. So an electromagnetic field can be perceived as just a magnetic field or just an electric field, but if you start moving something around it, then for this moving object, it will already not be just an electric field or just a magnetic field. It will become an electromagnetic field. So here the same thing applies. Each field generates the other one. And so this is how electromagnetic waves propagate through space. They generate each other and flow through space. So if we look at the electromagnetic wave, which is, by the way, light. Light is the most common electromagnetic wave that we know. Also X-rays, radio waves, they're all electromagnetic waves. So if we look at an electromagnetic wave from this direction, we will see that the electric field fluctuates in a plane. So this is called linear polarization of a wave. In theory, the electric field could have been just circling around and not fluctuating in a plane, as is shown here. But this is actually a more complicated case, as you can probably guess. And if you're looking at the sun, your eyes receive actually a whole bunch of different photons, which are light particles. You see, light has a wave-particle duality, which means that we can describe light both as a wave and as a particle. As a particle, it is called a photon, and as a wave, it is called a light wave, you know. Sometimes the electric field will circulate around the axis of the propagation of the wave, but in most cases the electric field fluctuates in a plane. and this is called linear polarization. Now, if we look at a wavefront, which is basically just a lot of electromagnetic waves, from this direction, we will see the plane of the electric field fluctuation for each wave. And usually we will see something like this, because the planes will be just randomly and evenly distributed across all angles. But in the case of a plane polarized light, or simply just a polarized light, all of those planes will be parallel to each other. And this plane polarized light can be generated by specific crystals, but the important thing here is that the plane polarized light is critical for stereochemistry, because this light alone lets us distinguish enantiomers of compounds containing stereocenters. Well, we'll get to that in subsequent lectures, don't worry, but just bear in mind that the plane polarized light for chemistry is very important. Now, I know that you're probably tired from physics, but the good news is that we're done with physics. This is basically all you have to know about physics. If there will be something else, I will just explain it as we go through our chemistry lectures. And now it's time to talk a little bit about math, just a couple of concepts, not as much theory as in physics, okay? But those concepts are nevertheless important. And so, let the math begin. All right, so this is the math section. And the first topic that we're going to cover here is spherical coordinates. Now, you're all familiar with Cartesian coordinates, which are for a 3D space, and they are denoted x, y, z. So what you do here is you draw 3 orthogonal vectors and assign x, y, and z to them in this fashion. And this system exists for uniquely specifying a point in 3D space by using 3 coordinates relative to the origin. So in some situations, spherical coordinates might be useful because they're just more convenient, okay, in some cases. So they are composed of 3 components, just as the Cartesian coordinate system for a 3D space, and they basically do the same thing, uniquely specify a point in 3D space, but they use different coordinates. So the first coordinate is a radius. This is basically the distance between the point that we're considering and the origin, okay, the center of the coordinate system. And the other 2 coordinates are angles between the axes, which can be assigned x, y, z, as in the Cartesian coordinate system case. So the phi angle varies from 0 to 2 pi radians, and it denotes an angle at which a projection of the vector to the xy plane is situated relative to the y line. All right, in this case it's left part. And the theta angle specifies at which angle this vector is situated relative to the z-axis, okay? So this is basically it. We will be using those spherical coordinates when talking about electron density distribution, which will be described in the next lecture. And now let's turn to the last, but certainly not least, aspect of math, which is probability density. Now, I know that this thing can be really hard for someone to grasp because it involves a college level math, but it is not actually that important for chemistry. If you don't come to grips with it, don't worry. So first, let's talk about probability. As you probably know, if you toss a coin and then catch it, you have an equal probability of getting either heads or tails. And if we set the total probability to 0, the probability of heads and the probability of tails will be at 0.5. In this case, we can create a random variable that would take values of, say, 0 when we get heads and 1 when we get tails. And the probability of 0 will be 0.5, and the probability of 1 will be also 0.5. But this random variable has only 2 possible values. But in more complicated cases, if we look at random variables that vary not within just a set of 2 values, but within a set of infinite number of values, as in this case, here it varies from minus infinity to plus infinity, okay? We can't define a probability for each value, because for each value the probability will always be 0. It is so hard for the random variable to become equal to one value when there is an infinite number of other options. So for these variables we define a function which is called the probability density. So the probability density is a function which sort of represents the probability across all the values, and it is possible to define such a function because we get it by differentiating another function, and we won't get into details here, but you gotta bear in mind that if we integrate this function from minus infinity to plus infinity, we will still get the total probability of 1. If you don't understand integral calculus and differential calculus, don't worry, you won't need to understand it in future lectures. We'll actually get back to probability density in the next lecture in order to understand the wave functions better, but if you don't get this, it's totally fine, especially if you're in high school, so don't worry, your progress in chemistry will not be hampered by not understanding the probability density, because this is a daunting math. I understand it perfectly. So this is it, guys. I hope I have clarified some things for you in this video, and I also hope that this video will enable you to understand the course better. So if you like this video, give it thumbs up, subscribe to my channel, and stick around till the next episode.